yesterday, right? Last class, right, we had discussed about the various branch predictions. So of that, right, 1-bit branch predictions, 2-bit branch predictions, and then right, we just move for correlations, branch predictions, right? Or we can say it as a 2-level branch predictors. And it just we have solved a few problems on this also, like how 1 and 2-bit is going to work and what is the need for correlation branch predictors. So actually the need is what, suppose sometimes, right, it is depend on the previous branch outcomes. So most of the branches, it's depend upon the output of the previous branch. In such cases, right, this correlation or 2-level branch predictor is going to help. Okay, so that's why, right, we have seen something like m comma n. So this m represents was last m branches. So if you want to predict any one branch outcomes, so it will just try to relate the last m branches outcomes. So based upon that, it will try to predict whether the branch is going to happen or not. Okay, so ultimate aim is what, just to reduce the control hazards, because when you just go with the pipeline, we have 3 different stalls. One is the data stalls, structural stalls, and the control stalls. So we have to reduce those 3 stalls in the pipelining. So compiler technique is the one way to reduce the data hazards. And right, this dynamic branch prediction is where, right, we are just going to try to avoid the control hazards. So which means, right, rather than just filling up the pipelines without knowing which branch is going to get executed. So at the decode stage itself, we will try to predict like what branch it is going to execute, and accordingly we will try to load the instruction. This is the idea behind that. And we have multiple branch predictors like 1-bit, 2-bit correlation branch predictors. So these videos for the English section students, maybe SAR may continue, or else, right, I will post the video to your classrooms. You just kindly check out. Okay. So today, right, we will go for the other branch predictors, which is called the tournament branch predictors. Okay, this is the advanced level, and almost like all the processor is having this tournament branch predictors. So with respect to correlation branch predictors, you know this part. So only this is, this part, right? This part is the correlation branch predictors. Okay, so on the day we are seeing, right, we have a program counter, we have a history table, and we'll have the local prediction table. So what's the need for the history table? What it contains? Can anyone answer? What the history table contains? Is it containing that? History table will contain that? Okay, only local prediction table, right? That will give like from that only we are going to take whether the branch is going to be taken or not. Okay, so the same, this will contain what, last m branches, outcomes of the branches. Okay, last m outcome of the branches. So based upon that, only with the prediction table we will get to know, right, whether it has been taken or not. Okay, but here the restriction what is here, last m branches. So which m branch it is going to maintain is the question. So for that we gave the answer, which m branches, whichever is having the same k bit, isn't it? So because we hope you remember on that day. So for example, if we take the program counter, it may takes the value like this 11100 or 11100. So any branch will be like this: branch 1, branch 2, branch 3. So those program counter may be anything, isn't it? So what this correlation branch predictor will do is, it may take any k bits. So there is no restrictions. It is purely depends upon the size of the history table. So the maximum is 1024 into 10. So this case, right, we will take this 3. So whichever is having the last 3 bits, 3k bits same. Okay, so you may have other branch. Suppose that branch may be 110. So this may not refer to this table. You got it? This branch may not refer to this table. Only the branches which have last k bit same. So those can communicate with this, and accordingly it will make the predictions. So this is the problem with correlation branch predictions. So because the one with the same PC, this k bits, it is not a good solution, isn't it? Okay, because based upon the branches, we need to take it. It is not with respect to the PC's bits, we have to make the decisions. Understood or not? So we have discussed the problem like this. So this one, right? If A is something, we are making some value, okay, something we are making A equal to 0. So yeah, similarly, if BB is something, we are making BB equal to 0, and next we are checking if A is not equal to BB. So we are doing it. So what is that assumption we made is if this 2 is not taken. Sorry. If this 2 branch is not taken, so this is going to take. Definitely this will take, isn't it? Because if it is taken, it may be 0. If it is taken, it may be 0. So probably this is not equal. If both is not equal, so probably right, this there is a chance for higher probability to branch. Suppose right, only if all the addresses of the same thing, then only right we will have a dependencies. All the branches will check onto the correlation table. Suppose if this address is 101, this is 102, and this is 103, will it be feasible? Not 101. Write it in binary like 110, 111, something. Okay, so 100. If this address is different, so definitely right, these correlation branch predictors may not work. So that's why right they move for something called the tournament branch predictors. Clear? So clear. So here we are going to see when you just go with the tournament branch predictors, instead of taking the last m branches outcomes, so we are going to use the outcome of the last m branches which is of same or different PCs. So that is the aim here. Okay. Suppose right, if you are given as a 12 bit, so it is going to take last 12 branches, keeping track of the outcome of the branches in the program, irrespective of the PCs. It may be, this case, right, the K bit we have, right? So whatever the case, it won't consider, irrespective of these things, same or different. With the help of this global history table, this one, this side, okay, global history registers, we are going to predict the outcome of the branch. Clear? So this is the idea. So clear, when you go with the correlations only, it will take the last k bits, whichever the branches, m branches with the k bits equal, only those things it can able to predict it. Instead, what we have to do is we have to take the outcome of last m branches, but it is not the thing that it should have a same PC. That's the aim over here. Okay, so when you just go with the additional hardware that are essential for tournament branch predictors, we have these things. Okay, local history table, we have program counter and local prediction. This is from correlations. And apart from that, we have these three more components. One is the 12-bit global history registers. Another one is the global prediction, and another one is the choice predictions. So these three are the three more components that is added to the tournament branch predictors. So when you just go with the global history registers, you just write on, so it may contain the latest 12 branches. So just which is keep track of outcome of a few branches. It depends. So maximum is 12. It may be 3, 4 or whatever it is. Okay. So few branches in the program. The most important is with respect to PC, it may be same or it may be different. Okay. So this is the place it differs from the correlation predictors. Okay. So there it should have only the same pieces, but here it is not the same. Okay. But when you just go with the LHT, local history table. Okay, if we take local history table, so here right, it should maintain the outcome of the same branch. So that's the problem. Okay. So this will maintain the outcome of the same branch, but global history is going to have the latest 12 branch. And here it is similar to local history, so global thing is there. Here we have one more thing called the choice predictions. So what does choice prediction, when it may be helpful. Okay, so now, right, I mean, when you just look onto the architecture of tournament branch predictors, see, local history table is also giving the output, and the global prediction is also giving the output. Now, right, we have a max. So you know the operation of the max. So now we have two input and one selection lines, and basically, right, which has to be chosen is going to be the questions. So the thing is, right, when both the thing is same, it won't be the problem. Okay, suppose, right, if the local prediction is going to be output of this is, it's going to be not taken, and this is also not taken. So probably the branch prediction is going to be the same. If suppose if it is going to be one, or again if it is going to be one, again the branch is going to be taken. So here also no problem. The problem arises, so this case, suppose, right, assume that the output from the local prediction is 0, which means it is not taken, but the output from the global prediction is taken. So if you have this, now, right, the choice prediction has to decide which thing you have to choose, whether we have to take the local predictions or we have to take the global prediction outcomes. Understood? If both outcome is same, it won't be a problem, but if it differs, we have to depend upon the choice predictions. So how we have to depend, so that is going to be the question. Okay, so say for example, here, right, when you just go with the local prediction, maximum is 3 bit. So assume that in case of local prediction table, outcome is what? Is a 3 bit. So since it is 3 bit, so what we need to do is we have to take some value, because we know, right, in case of 2 bit what we are doing it, in case of 2 bit, right, if it is 0, it is 1 0 and 1 1, we are taking it as a taken. Okay, similarly, right, so in case of 3 bit, if you just go with the 3 bit, if it is greater than or equal to, sorry, uh, sorry guys, okay, so assume that if it is going to be 3 bit, if the value is greater than or equal to 4, it is going to be considered as taken. Clear? If it is less than 0 or 0 to 3, because the 8 possibilities, isn't it? When it just go for 3 bit, it is going to be 8 possibilities. So out of that 8 possibilities, 0 to 3, the value what we got is still between 0 to 3, it is going to be not taken. If it is greater than or equal to 4, it is going to be taken. Clear? This is for the LPT. Similarly, right, when you just go with the global prediction table, I mean, here also we have a global prediction. So the same sound, if it is 2 bit, so here, according to this is going to be 2 bit, this case, right? Since it is 2 bit, so if, I mean, so hope you know, right, if it is greater than or equal to 2, it is going to be taken. 0 to 1, it is going to be not taken. The next one, choice prediction. One second, Ma, I'll put the charger. One second. With respect to LPT, if in the case of LPT, right, if the value is greater than or equal to 4, it is going to be taken or not taken. And when you go with the GPT, right, 2 bit 0 and 1, it is going to be not taken. Greater than or equal to 2, it is going to be taken. So as I discussed, in both the cases, if it is not taken or taken, it won't be the problem. So now, right, when the choice predictions comes into picture, so if it is different, okay, when it is different, so again the choice prediction is also what, the 2 bit, isn't it? So when you go with the 2, I mean, in case of choice prediction, if the value is 0 or 1, it take the output from the local history table. If the value is either 2, 3, it will take the output from global history table. This is the place where the choice prediction circuit will play. Understood? Okay, 2-bit, and clear or not? Don't get confused. 2-bit means we have 4 values, right? 0, 0, 0, 1, 1, 0, 1, 1. So in this, right, if it is 0, 0 or 0, 1, it is going to be a local history table. It will take the output from the local history table, and accordingly it will do the branch predictions. Or else, right, if it is 2 or 3, it will consider the output of the global history table. Okay, understood. So I mean, based upon that, as we did in correlations, once we predicted, again all the changes we have to do, we shift the global history table, so, all those things. Similarly here, as we are doing here as global history, local history, and global history registers has to be done, and all the prediction bit has to be updated. We will see how it has to be done. Next step, we'll go with one problem and we will see it. Okay, so till now, with respect to architecture of tournament, any doubt? Understood the need of the components that is there in tournament branch predictors. So additionally, right, we have this part: global prediction, choice predictions, and it will be global history registers. Just map it. Instead of local history, we have global history registers. Here we have a local prediction, we have a global prediction. The only extra component is choice prediction. This choice prediction, right, it will decide which outcome we have to take, whether we have to take the local prediction or we have to take the global prediction. When it differs, when the condition differs, when the output prediction differs, at that time only choice prediction will comes into picture. Shall we move on to the problem now? And with respect to problem aspects, I think correlation, hope you can, yeah, okay, they may ask anything. Okay, you may get a problem on either tournament or you may get a problem on correlation also. So they may give a loop, some statement or some if case statement they may give, and they ask you to find out the misprediction rate, as we did for like 1-bit and 2-bit. Similarly, right here also they will ask you to find out for misprediction rate. So you have to find, but everything will be given clearly. How many times the loop will be repeat, all those things will be given clearly, and accordingly you need to work. Okay. So now, right, we will take an example. So we have these things. Instead of those many entries, I think this is the maximum entries. Okay, 1024, like 1K entries. Yeah, 4096. 12-bit. Okay. So this many things we have, 4K entries and 1K entries. But right, just for an example aspects, we will take this these cases. Okay. So this is what this is the local history table, and this is the local prediction table, and this is the global prediction table, and this is the choice prediction, and this is the GHR. So now, right, currently something is that, let it be. Some has been, when we explain about correlations, we have started with some 0, 0, 0 also. So when you want to solve the problems, you have to start with 0 zeros only. Okay. So just example aspects. Just I taken it direct. I mean, I have taken this picture directly from the net. So assume that some status has been already recorded. So now, right, we need to decide what are all the steps we need to follow when you're just going for this tournament branch predictions. Okay, so assume that, I mean, here also, right, we have 3 bits. So we will take the last 3 bits. Okay, so this case, so last 3 bits from the program counter, because only with the help of the program counter only we can enter into the local history table. So keep remember this word, right? Only with the help of the program counter we can enter into local history table. So since it is 3 bits, so we have taken the last 3 bits. So when it is 3 bits, so where it goes, where it map 100. So right, it will map to this case. You understood or not? So it will map to 0, 1, 1. So here, right, since it is 0, 1, 1, again, right, here admin, it will make a move to the local prediction table. So in the case of local prediction table, it is what, 1, 0. I mean 3, right? 0, 1, 1 is 3. So it is going to this. So it is 3. Here it is 1, 0. So what is 1, 0? If it is 1, 0 in 2-bit, what does it mean?
2.
Is it taken or not taken?
Weakly taken.
Yeah, weakly taken. But yeah, it is a taken, isn't it? Okay, weakly taken or strongly taken. So this one. So remember it. Don't get confused. 0001 is not taken case, and 1011 is a taken case. So here it is 10. So it is a taken case. Okay. Output of this local history table. I mean, this one is the taken case. Now, right, we will take this GHR, global history register. So when you just go with the global history register, so what is the value? We have 1110. So 110. So it will goes to this part, isn't it? 110 is going to this part. So what is the value which is already there? Again 10. So according to 2 bits, since it is 10, the output of this global prediction table is also going to be taken. Understood? So now it is taken. So both the outcome is taken. So clearly, right, there won't be a confusion. Only if it is taken or not taken, then only it is going to be confusions. In this scenario, both is going to be taken. So probably, right, you will get the taken cases. Assume that our branch outcome is also taken. Okay, actual branch outcome is also taken case. So what are all the changes we need to do? On the day we did, right? So now right here we have to do a shifting. So what it has to be done? What is that value we have to do? Since it is taken, what we need to push? Push
One
1.
1.
on the
This
left
is,
side.
wow, 101. Okay, this has become as 101. So now right here it is taken, right? Because according to the state 0001 1011. According to the case, it is in this state, so we are taken as taken. But now since the branch is taken, it is moving to the strongly taken case. So this value will be changed to 1. Understood? And similarly, here also you need to push. Since in taken, the outcome is what? 1. So here, right, the global register has become as 111. And we referred as 11, so this will also be changed to 11. At the same time, this 6 bit also changed to 1. In global, in this branch prediction also, should it be 1 1? Because previously what it is?
101.
So previously it is 0 1. Now it has been changed to 1 0. Got it? So these are all the changes we have to do it once for one branches. Clear? So whatever the PC, using the PC, we need to enter into the local history, and from there we have to enter into the local prediction and we have to do the predictions. At the same time, depends upon the global registers, we have to go for the GPT and we have to take the case. Okay. So this after, I mean, if the outcome of both is same, then it won't be a problem. So we no need to consider the CPT, or else we have to consider the CPT case. Understood? Suppose we will take other case. Let it be. Say for a change it. So the PC is like 100010. So you take like this something. Okay, 100010. So again, right, last 3 bits we have. So what is 010? It goes to where? Okay. So it will go over here, right? 010, it will goes to this place. And it will go there.
001. Ma'am.
Yeah. Sorry. Okay. So it goes to 001. From 001, where it goes? Right? 001. Yeah, it goes to 01. What is 01? It's taken or not?
Not taken.
Is not taken.
Not taken.
Yeah. It is not taken, right? The output is not taken. Now we will go here. Here what it is? 111, because the GHR has been updated to 111. So 111, where it goes? It will go here, right? 111. It will go here. So what is there in what is there here? 01, isn't it? Since it is 01, here also it is going to be
Not taken.
not taken. Since it is not taken, our output is also going to be not taken. So assume branch taken is also not taken. So now, right, what are the changes we have to do? So since it is not taken, what it has to be done? From 0, 1, it has to change to
0.
0. Similarly, this should be changed to 0, 0. And here, from 1, 0, it has to change to 0, 1. It has been changed to 0, 1. So these three, and now we need to push this. So what is that we have to push? Since it is not taken, what is that value after this?
0, 1, 1.
0?
0, 1, 1.
0,
0
0,
will
0,
be.
0, 0.
Okay.
This means,
Yes.
right?
Mm.
So 0, 0, 0 we have to push, and here what is that value we have to do?
0, 1, 1.
0, 1, 1. Understood? Okay, so these things we have to do it. Suppose, right, again assume we will go with the same case. I don't know what the output is going to be, but we will check it out. Suppose if it is 100, so where it goes now? Change the color.
101.
Okay, so now it is 4, so it goes to this. So where it goes to 101. What is 101? Where it goes? 1015, right? Okay, so 101 it goes to 00. So since it is 00, the output of this is going to be not taken. And here, right here, what it is 011. 011 where it goes? So 011 is this case, right? Yeah. So since it is this case as 11, now what is that? Since it is 11, it is
Taken.
taken, right? Got it. So now we got it. Now this is what? This is not taken, and this is taken case. So here now what we need to do? We have to depend upon the choice predictions. So when you go with the choice prediction 011, what is 011? 011 3, right? What is 3 part? I think this one, right? 3 is 3, 1 0. So when it is 1 0, which output we have to consider?
Taken.
Yeah, right? Because 0001, it is for LPT. So when it is 1011, it is for global predictions. So since the output is 10, we have to consider. So obviously, right? What will be the output here? The output is going to be taken case. Understood, Anna? So here only, right, the branch prediction comes. And accordingly, right, we have to make a changes here. Here we don't know. I mean, just for the simulation aspects, I have written and I'm just showing it. There, right? You may have the exact problem. You may have a loop, clear loop. They will give, like assume for I equal to 0, like for all those things, and they will give the 3 branches, and you know the actual outcome of the branch. So we have you find out what is the actual outcome, what is the predicted outcome. Okay, what is the actual outcome, what is the predicted outcome? Accordingly, right, we have to calculate the misprediction rate. That is very important. Since whatever the outcome comes here, I'm just considering it as true. I'm just writing it as it is. But I mean, when you just want to solve, when you are going to solve the real-time problem, you know what is that actual outcome is. Accordingly, you have to do it. Okay. So I think this is the way this tournament branch predictor will work. I think the other section people, now you got the rough idea. Only this part here, right? We did these many things. Instead, right, only this part. In case of correlations, only this part only you are going to do it. Similar step will be there. The only change is this one. So PC, whatever the PC address, irrespective of the bits, we are just mapping here. But in case of correlations, only the last k bits, whichever is equal, only we will map that. That is the only difference. The rest of the functionalities are same. Okay, so when you look onto the video or when Sir teaches about that, so you will understand clearly about these branch predictions. Okay, so That's about the branch predictions in our textbook. Okay, so just they have focused with the two branch predictors. One is the correlations, another one is the tournament branch predictors. And previously, just to make it clear, I explained about 1 bit and 2 bit. So you may expect problem on all those things. I'm just saying you will get only problems. You will never get the theory on first unit. 1 and 2, I think even second unit also you won't get theory. Maybe till the 3 and 4 is completely going to be like it's a vague theory only. Uh, Maybe within 3 days those two units will be completed, and again most of the topic you read in paper will repeat there in fourth unit. Okay, so only first 2 units it will be interesting just to solve the problem like this. So any doubt you have it, you can ask, or else we will go for solving that problem. And tomorrow we don't have a class. Saturday, in Monday, you are having a test. We are in discussions whether to conduct that test during the class hours or after 6 o'clock. What the others are doing? Are they conducting during class hours or evening?
After class, ma'am.
Yeah, okay. We'll also follow the same procedure. So maybe right, the exam should be scheduled after 6. Okay. So maybe 6. We will look into the complexity of the questions. So based upon that, we will allot the time. It may be either half an hour or it may be 1 hour. Hardly 1 hour it will be. So be ready. That chapter 1. Okay, you have a test on chapter 1. Not these things. Okay, only chapter 1. You just look at the chapter 1 questions.
Monday, ma'am, exam.
Yeah, Monday only.
Ma'am,
Okay.
That means, which means?
Timings, ma'am.
Timing just now I told you, right? After 6. 6 to 7 is our test.
Okay, ma'am.
Not during classes.
MCQ only.
Yeah. You want only those things, isn't it?
Ma'am,
Maybe the second test we will try to change something. I don't know because we have somebody is going to set the question paper. I haven't looked at the question papers. We will see. And then second CA will take it. Some twist will have the question. All because of the culprit who are not attending the class. For those people only. Such a worst response. This is the first time I'm having that thing in my class. Okay, now right, we shall. I mean, we will move on to the. I hope you don't have a doubt, isn't it?
ma'am,
Yeah, ma'am.
for global prediction table, the values are assigned by us or their default values.
See, initially, right, fresher it will be as 0, 0 only. All will be 0, 0 only, ma. I just for a sample case, I have taken these values. Initially, all will be reset to 0, 0, 0 only. After that, according to the branch outcomes, these values will be changed.
Okay.
Because in correlation, right, on the day.
Yes,
We are
ma'am.
taking fresher. Okay, it will be like that only.
Okay, ma'am.
Just explanation aspects, I have taken this. So for all the branch predictors, they will ask you to calculate the number of mispredictions for the given problem. Sometimes some groups will be given for that how many misprediction happens. This is what they may expect. So for that you will be ready. That's it. So now right, we will go to that this problem. Did anybody solve? We will cross verify how many cycles we got. I think when we saw students, did SAR solve this problem? I mean, not this problem, similar kind of problem using compiler. No, just now, did SAR solved problem on this completed next? You only responding to all the message. Yes, alert. Just now. This Manoj, I mean, you're the guy that you are in my digital class, isn't it, Manoj? It's all solve this problem. I mean, this problem. What is this? This problem. Okay, if you know, if you have learned, just kindly follow up. Okay, so right here, the major thing is right. We are going to schedule the instructions. I mean, not we. We are just see how the compiler is going to schedule the instructions to avoid these stalls. Number of stalls that is available. I mean, in the pipeline. Okay? So we'll see how the compiler is going to schedule this. And they are given clearly. They are given the latency table. So you suppose if any instruction is depend upon the output of the previous instructions, how many cycles it needs. That has been given here. Suppose if you have a multiplication instruction and this one, if you have a multiplication instruction and if it is followed by an add instruction, so it has to wait 6 cycles. After 6 cycles only, this add may get the output. Okay, so obviously, like the pipeline has to wait for 6 cycles. So our aim is like this cycles has to be reduced. So one or other way we have to schedule the instructions, thereby the number of cycles has to be reduced. So that is the objective of the compiler. So on behalf of compiler, we will see how it is going to be done. So if you take this problem, okay, so and be careful. One mistake commonly what we do is we will just roughly we will look at the okay, load is followed by null is followed by load. So I mean, don't go with that assumption. You just find is there any data dependencies. If you have a data dependence only, you will have a star, or else you don't have a stars. Understood? Clear? So suppose right, if you take this instruction load and mul, okay, you have a data dependence because whatever the load is going to load, only those value it is going to be used by this. So probably right, there is a dependence here. Okay, so assume that this is one data dependence that is existing here. And when you just go with this case, mul and d, is there any dependence between these two instructions? Is there any dependence?
No, ma'am.
No, right? Between mul and load, there is no dependence. But if you take these instructions, whatever, when you take these instructions, whatever it is going to be load, the same thing is going to be used by F6. That is one case. The other case, see, when you take, sorry, not this F6, okay, this F6. Okay. So whatever it is going to load, this is used by this. And again, where is F4? Where F4 comes? F4 comes from multi. So this is the other data dependence. Understood or not? So here, right, we have two data dependence here, D2, D3. So two data dependence. And similarly, right, after that, again, there is a data dependence between these instructions. Whatever it is adding, the same thing is going to be stored. So there is a data dependence here, another data dependence. And here and all, there is no dependence. So directly, right, it can do it. But if you take here, again here we have one data dependence because it is just testing based upon that only we have this. So again here also another data dependence. Clear? So right, So based upon the dependence only, we need to go for the total number of stars. Now write.